with you, David.
Okay, thank you, Max. And if there are any technical troubles, just interrupt me and let me know. So thank you very much for the introduction. So my name is Dave Hoogerheide. Yeah, I'm an instrument scientist at the Candor Reflectometer at the NCNR. And of course, what I'm going to tell you about today, we haven't had neutrons for a year and a half. So what I'm going to tell you about today is simulated, but we're really looking forward to trying it out on a real instrument. So I want to especially thank Tom and Max and Brian for inviting me to give this talk today, to all of you for coming. Paul Kinzel, who I think many of you know well, wrote the Refl1D software, which is sort of the engine for all of this. And I especially want to thank my colleague Frank Heinrich, who introduced me to the whole kind of information theory type thing, information approach to reflectivity data. And a lot of this is inspired by what he's done. So about a year ago or so, let me see if I can get this to go. Here we go. About a year ago, Frank and I attended a workshop at Lawrence Berkeley Lab in the US. Here was a virtual workshop on autonomous experimentation. And a lot of the approaches that we heard there were related to solving big Bayesian integrals. And we're like, this is basically what Refl1D does. I bet we can take the output of something like Refl1D and turn it into an autonomous engine. So I really want to give credit to this particular workshop for sort of inspiring this and kind of showing us that this is possible. So to start out, I'd like to just give an example of a reflectivity curve. I know to this audience this is a little bit trivial, but I chose this particular example for a couple of reasons. One is that most of the simulations I'm going to show you were actually done with this data set. And the other reason is it illustrates, I think, some of the levels of decision making that go into a reflectivity measurement. So this is a fairly standard, I do biological reflectivity measurements, and this is a fairly standard type sample. So this is a silicon substrate with a sputtered titanium oxide film, and then a lipid bilayer, which is mostly hydrogenous in the center, and so it has a low scattering length density, is sort of deposited on the surface. And a typical experiment flow here would be to measure this in two different isotropic contrasts. This is done in a liquid cell, of course, and so the surround here is either D2O or H2O, and of course it can penetrate in different parts of the structure. By doing a joint optimization of these two in these two isotopic contrasts, we can get a better handle on some of the structural parameters. So the data are shown here. This is taken on the MAGIC reflectometer at NIST. This is a monochromatic reflectometer, so we're taking these data point by point. And so this is kind of what our data look like for D2O and H2O. The solid curves correspond to the SLD curves here. This was published in a different context last year. The underlying model for the scattering length density curve, and again, this is probably something that most of you are familiar with, is one of these component volume occupancy models where we basically fill up all of space with the various materials that make up our sample. So here's the silicon substrate, here's the silicon oxide, here's the titanium oxide, and then this is what we're interested in, is the bilayer itself. And these are the different components of the bilayer, each of which has a unique scattering length density, which is why they're broken out into these different components. And we have, in this particular model, we have 16 parameters, only 5 of which we care about, and those have to do with the structure of the bilayer, how far it is from the surface, how thick it is, how much water is in it, that sort of thing. And then 11 of the other ones are ones we don't care about, right? They're all substrate parameters. They're scientifically not interesting. And so these are the ones, these 5 are the ones that we're really interested in for this experiment. So this is again, the reason I chose this particular example is because it illustrates some of the levels of decision making that you take when you do a reflectivity measurement. And of course, the top one is really scientifically driven. What samples do I run? Right? What are my film properties? How do I prepare the substrate? But then here's a sort of technical one. To get the information that I want, what isotopic contrast do I use? D2O, H2O, some mixture of them. Do I perdeuterate my molecules? This sort of thing. So this is a sort of high level decision having to do with how you actually prepare the sample. Then once you've decided that, you say, well, how much data do I need for each of these? How long do I measure each of these different, for example, isotopic contrasts? how much time do I spend on a given sample? What's enough, right? And then there's another level underneath all that. Once I've decided which isotopic contrast and how long, how do I actually go about collecting that? What's my Q spacing? How long do I measure at each, or my binning, or what wavelength range do I use, or something like that. Each one of these is, in principle, subject to some sort of AI, machine learning, or active learning type approach. And I wanted to put this up here to just say that we're really going to focus on this blue one on the bottom. How do I actually go about collecting my data on a sort of fundamental level, with a little bit of bleed over into this one about how much time I should spend on a given sample. So that's kind of the the scope of what today's talk is going to be. So this is a sort of typical workflow for a reflectivity measurement. I've coded the different the different steps in the workflow by things that the user has to give input, things that are controlled by hardware or instrument control software, and then sort of analysis or offline software in orange. So the first thing we do is we say, to collect a reflectivity curve, I'm going to define a set of instrument configurations. In our parlance, we call this trajectory. I'm sure you have your own word for it, but it's a set of instrument configurations. It's a list of things that the instrument's going to do. You give it to the instrument. It goes and collects data. Then we reduce the data, analyze it, and here we need some more input. Typically, we'd have some sort of physical model of what the scattering length density profile should be and how this corresponds to physical reality. And again, here we can identify some parameters that we're interested in, and often some nuisance parameters. For our monochromatic reflectometers, for the example I showed you before, we have even spacing in Q, tighter at low Q, so we can get the critical edge a little bit better. This is a constant footprint measurement, so the intensity scales as Q squared, reflectivity drops off as Q to the 4. And so typically we spend about our time at each point scales as Q squared. We'll revisit this a little bit later in the talk. Oops. And then for each instrument configuration, we've got well-defined collimation. And we have to do this because of the footprint, constant footprint measurement. When we design this experiment, really our goal, and this is true whether or not we're using machine learning or not, is to maximize the rate that we can acquire information in the measurement. Right? So this is sort of a common goal for everything. For this particular talk, we're going to make an assumption. And this is that some parts of Q space are more efficient than others at constraining our parameters of interest. Now, you know that this is true, because if you go to really high Q where your signal to noise is bad, clearly this is not going to be a place to measure if you want to efficiently constrain a model. And also at very low Q, for example, below a critical edge, you don't actually get any structural information. So you know that there are some regions that should be avoided for lots and lots of measurement. But then what about in the middle, right? You have this real space scattering length density profile. You do this physical Fourier transform, which is your scattering measurement. Then you square it, right? So you lose your phase information. It's even worse. And so it's not immediately obvious that this would be the case, that you can actually choose some regions of Q space because you're sort of spread your real space information out everywhere. But let's assume for the moment this is the case. And if in that case, what we want to do is we want to measure in those regions of Q space that are most efficient. The problem is we don't know what that is when we first start our experiment, right? We don't know what the structure is, so we can't identify what those regions of Q space are. So this is a perfect application for an active learning approach. And the way that you do that is you introduce some feedback into your loop. So now your set of instrument configurations is not where you're going to measure, but where you could measure. So you collect some data, a limited amount of data, you reduce it, you analyze it to the best of your ability. And then for this talk, you're also going to define a model on your parameters of interest and use this to identify the next data point. And this, in the end, this ends up being a calculation of something I call a figure of merit that basically says how advantageous is any of the possible measurement points that you could have. And in the best case, this would be specific to the parameters of interest, which in the Bayesian language would be called marginalization. Since we're talking about information, let's put a little bit more specific definition on that. And the idea here is that if a parameter of your model is well constrained, it will have a narrow width, and you have a lot of information about that. On the other hand, if it's broad, then you don't have much information on that. And you can quantify the gain in information after measurement by comparing the width of the prior to the width of the posterior. And this is your sort of, this is your information gain for a particular parameter. And so this is assuming a Gaussian posterior and a uniform prior, and then you get this expression. If you want to extend this to multiple parameters, which now could be cross-correlated, you use something called the covariance matrix. And in this case, it's the negative logarithm of the determinant of the covariant matrix. And this is a particular style of calculating information called the multivariate normal. So it assumes that all of your posteriors are normally distributed, which is of course never true, or rarely true. But one of the themes of this sort of active learning thing is that perfect isn't necessary. Good enough is good, and so this actually ends up working quite well. If you want to marginalize, you just take the rows and columns of your covariance matrix that correspond to your parameters of interest, which I call X prime, and it's a fairly straightforward calculation. You're just using a submatrix of the full covariance matrix. And I'm going to call this information gain of the marginalized parameters delta H marg. So the active learning strategy here is to maximize the rate at which you improve delta H marg. So this would be the information gain at a particular measurement instrument configuration divided by the amount of time it takes to actually get that information. So this is really a rate, and this is what I'm going to call the figure of merit. This is the thing we want to optimize. At each measurement point, we want to measure at the point that's going to give us the highest information in the least amount of time. The strategy here is straightforward. You search through all your possible instrument configurations. You can put them in a vector called X. For our monochromatic reflectometers, where we're measuring point by point, this would just be Q. We use any data that we've collected to date to produce a best guess for the count rate at each Q. We calculate this figure of merit using that information. And we can calculate the figure of merit from that information. I'll show you how that works in the next couple of slides. And then the feedback loop just works like this. You measure a data point, you fit it. In other words, you sample the parameter space constrained by that new data point and any other data you've collected already. You recalculate your figure of merit to identify the next data point, you repeat. So how does this actually work in practice? What I'm showing here in the upper right is a plot of reflectivity on a Q to the fourth scaling as a function of Q. It's unconstrained at the beginning of the experiment, except it is constrained because you've given it a model with some limits to the parameters, for example. So this is basically a random sampling of all of the possible solutions in the absence of any data. You can still calculate a figure of merit for this, and you choose the maximum point, and you go and you measure there. Then you recalculate the family of curves. Now with this new information, you get a different figure of merit, and you go and you measure there. And now what you see is that when you analyze it again, the data are actually constrained in the model, and you're starting to get some information about your model. Okay, so that's basically how it works. Now, how do you calculate the figure of merit? And this is a particular implementation using REFL1D, which is a Markov chain Monte Carlo sampler. What you're doing is you're sampling a distribution in parameter space that is defined. So X is your are all your parameters, and the probability of getting that is this expression, exponential, and the chi-squared values. In other words, so the data are actually constraining your parameters. Each of your possible samples so when you fit your data, you get a distribution in parameter space that obeys this distribution, and each one of the samples that you get corresponds to a R of Q curve, which isn't necessarily the correct R of Q curve, but it's one of the ones which is close, it's constrained to the data. And so what do I mean by that? Here's a simple example of parameter two parameters, parameter 1 and parameter 2. This is, of course, completely made up. But let's say this is what your posterior distribution looked like. In other words, these are your data constrained parameters. In this case, they're clustered. They don't have to be, of course, in general. And each one of these dots corresponds to one of these curves in R of Q versus Q. The ground truth here in the parlance of machine learning is the black curve. So how do we actually do the information calculation? Well, you go through each, in this case, Q point. It could be a more generalized instrument configuration, but in this case, it's Q. You go to each Q point, and you look at the distribution of R of Q at that point, which looks something like this. And you assume that if you were to measure there, you would measure at the median of this distribution. That's your best guess, the median of the distribution. And then you say, I'm going to measure for long enough that I can exclude the tails of the distribution. So I'm just going to keep the samples that correspond to the inner 68%, for example, kind of 1 sigma either way, of this distribution. You can choose whatever value you want for this, but I just chose 68% for this. Then you look at your parameter space and you say, which ones did I throw away? In that case, this is the blue dots are the ones I threw away and the red ones are the ones I kept. And because the ones I threw away are evenly distributed through this distribution, I actually didn't get very much information from doing that, right? So this would be a low delta H measurement point. On the other hand, if I could find a point on this bottom row where I do the same procedure, I assume I measure at the median, I throw away the tails of the distribution, and when I do that, I've selected one of these clusters relative to the other. Now I've gained a lot of information about my parameters, and this would be a high information point, okay? Now, the other thing you have to think about when you're talking about information rate is how long it takes to actually get there. And this is something that you can know from your characterization of your instrument. If you have a width of the distribution sigma 0 squared, so that would be the width of this black line, to reduce that width of the P of R distribution here to a smaller width sigma, you have to count for a time R delta T. And R is the rate at which you're actually measuring neutrons. So that would be R of Q times the incident intensity at that point. And so you know that, you know your instrument, you know what the intensities are at least approximately. And so you can calculate what the rate is, you can calculate what delta T is. The other thing you can do, of course, is you can include things like movement times, because delta T is not only the amount of time you spend measuring, but also the time it takes to get there and any other things you have to do to your instrument to collect data at that point. Okay. This is where the actual information about R of Q comes in. And again, you're assuming that you're measuring at the median, so that's the R of Q that you choose. And then it just becomes a matter of taking the ratio of the two. At each Q point, you now have calculated an information gain at that point. You've calculated an amount of time, delta T, that it takes to get there, and you look at the ratio and you select the best one. And so in this particular example, this one was this one, for example, it might take a long time to get there because you already have a small width of your distribution. So you might have to count for extra time, even though it's a high information point. You might want to choose a more intermediate point where the reflectivity is higher, the intensity is higher, but you don't get quite as much information. Okay. So I think you get the idea. You just do this at every point and you choose the best one. One of the advantages to this particular algorithm is that once you've done your selection of your point and you've thrown away some of your samples, you can actually just do the process again. So you can forecast multiple steps into the future. And we could talk more about that if you're interested. I'm not going to go into it in a lot of detail now. You can include movement time costs. I think I said that right. So this is what it looks like if you run this simulated experiments. This is the D2O data set that I was showing you before. It's just stepping through, and for every step here, we're doing an analysis of the data, recalculating the figure of merit, and choosing the maximum value. Now you'll notice sometimes it's not choosing the maximum value, and that's because of the movement time costs that are implemented here. But it's choosing the optimal value that gives you the most information in time. Now I'm showing here on the right-hand side two plots. This is the information change as a function of log T, and this is marginalized on the top panel and the total information in all the parameters on the bottom panel. And I'll talk about the black curve in the next slide. So a couple things you'll notice: the points where it's measuring are concentrated in particular areas of the reflectivity curve. You can see it's getting more and more constrained as it measures more points. There are a few points it avoids, these minima, for example, where there's basically no reflection. And even one here where there is plenty of reflection, but it can do just as well by measuring the points around it. And this is because the model is telling, it knows about the correlations between, for example, this Q value and the ones adjacent to it based on the model. Okay, and you can let that run as long as you want. All right, so let's talk a little bit about performance. It's always a little bit tricky in these sorts of problems to figure out how well you do. And so here's a couple of ways of going about doing that. Let's say you took the sort of naive approach, and there's a typo here, it should be q squared, and you said, I want approximately same delta r over r over my curve, and so I'm going to measure in this particular experimental setup with the time I spend at each q value going as q squared. So that's what this black curve is. So if you just take one of these points in the black curve, this is the total measurement time. You spread it out over your sort of predefined q points that you usually measure in, and such that the total measurement time is whatever this point is, and then you do the analysis with REFL1D, you figure out how much information you have, and that's what that point is. The blue curve is what I was showing you before, the amount of information is a function of time from the autonomous measurement. And so the speed up from doing the autonomous measurement is in fact this distance in the log t space here. And this turns out to be about a factor of 6 at long times, and even better at short times. Okay, so this is a really remarkable speed up over the sort of naive time scale. Now, of course, we have something working for us. The type of sample that that the simulation is based on is a pretty common one for us. And so our organic intelligence has been working on this for years, and we actually have a current best practice, which is not the same as this expression. And if you try to look at the speed up relative to that, it's not as good. And that makes sense because our current best practice is in fact the result of years of experience. But we still get about a factor of 50% to a factor of 2 speed up over that best practice. The other way that you could calculate performance here is by saying, what if I were to just measure a random point instead of the best one? So then you calculate your figure of merit and you look at the maximum, the ratio of the maximum to the average for every step. You average that out over the experiment, and you get about a factor of 4. So this is a pretty good estimate for the performance speed up. I would just like to point out that even relative to our best practices, the autonomous measurement is doing better. And so I would say that this sort of sets the standard for the measurement efficiency. It's possible that my algorithm could be very much improved. So this might not be the best you can do, but it's certainly even doing better than our best practices. On the other hand, our organic intelligence does pretty well for common sampling. One of the things you get out of this is a sort of real-time readout of your parameters, because you're doing the analysis at every step. You can see what your parameter errors are as a function of time. And so we'll talk a little bit more about this later, but if you wanted to say, I need to know this particular parameter at this level, you could stop the experiment when you got there. You can choose different parameters to select from. In this particular case, I'm comparing the amount of time that it spends at a particular value of Q for selecting the bilayer parameters, so marginalizing on the bilayer parameters, versus on, say, the intensity parameter, which is basically only constrained at low Q. And as you can see, it spends all of the measurement time here at low Q around the critical edge, and very little out in the rest of the Q space. Whereas if you're using the bilayer parameters to marginalize it, the information is spread out in Q space. And so this sort of shows that the marginalization is working. So what happens if you have something like a D2O and an H2O condition that you want to measure at? In this particular case, I'm assuming that there's no cost to switching between these, which of course is not realistic. But you can include multiple models. So you could also imagine this would be something like a spin up and a spin down channel and a polarized experiment or something like that, where there's little cost in terms of time to switch between the two. So there's no reason you can't do this. You just have a figure of merit for each one of these two conditions, and you measure it whichever one ends up being giving you the best information as a function of time. So you can do that. One of the interesting observations about this is for this D2O versus H2O measurement is the autonomous experiment spends about twice the amount of time in the D2O measurement as it does in the H2O measurement. And this makes sense because there's actually better contrast with the bilayer, which has the parameters we're interested in the D2O case. So this all sort of makes some intuitive sense. And you can also calculate the performance speed up, which is about almost a factor of 3 in this particular case over the typical experimental our best practices. You can see that there. I'm going to skip these two. Now, what about polychromatic instruments? So this would be Candor, which I assume you're all familiar with, but basically it's like a multiplexed monochromatic reflectometer where we can measure from the 4 to 6 angstrom wavelength range. And so now data come in chunks, and this would be an analogous case to time of flight instruments where you're using a broad wavelength band and you're getting multiple Q values at once. You can do the same thing. You can calculate the figure of merit. It's a little more complicated because you have to sort of calculate for each one of your detectors or each one of your bins and in your time of flight measurement, how much information you're getting, and then do some kind of rational combination of those. But you can do the same thing, and you can run the experiment on a polychromatic instrument as well. So this is showing what that would look like for candor. If you try to look at the performance, so this is interesting to me because we don't have best practices for candor yet because it just came online. We don't have a lot of experience. So actually, compared to our current best practice, we do about 4 times better with the autonomous measurement than we do with our sort of poorly informed organic intelligence. But if you use this metric where you compare the maximum figure of merit to the average value, you see about a factor of 2 improvement. So this is basically, optimal versus random. And this is worse than magic. And this makes sense because if you go to the optimal point, because you're measuring a wide band in Q, you're going to get some suboptimal points along with the optimal one. So you still do better, but there's some degradation when you have the polychromatic, and that's kind of as you would expect. So here's a completely different system. I can't tell you what it is because this isn't published yet, but basically we're trying to distinguish between these 2 curves, the dark blue and the light blue one. And for this, if you run this at the autonomous simulation versus our current best practices that we would normally use to collect these data, you get an even better speed up, about a factor of 15. So this shows that if you have a sample and you're not so familiar with it, the autonomous measurement can do even better. The flip side is your model might not be any good. So, there's definitely a trade-off there. So let's talk a little bit about how one might use this in practice. One of them would just be experiment planning. This is a case where I allowed the Q range on candor to go out to a sort of ridiculously high value and looked at where it spent its time. So this is the number of detector hours at any Q in any Q bin. And you can see that it drops off significantly above 0.3. So it says, for this measurement, don't go above 0.3. Guys, this is a nice experiment planning use case. Keep in mind the signal to background ratio is in the calculation. This is a really important point. But of course, what we really want to do with this is instrument control. Try to get faster real-time data collection times. You also get some real-time user I/O capabilities here. You can monitor your parameters as a function of time. If you're deviating from the model that you thought it was, you can change it mid-experiment, no reason not to. You can also monitor your fit quality for the onset of some systematics or model fitting issues. And maybe you'd want to terminate the experiment if those started getting too big. And from an instrument scientist perspective, your experiment ends with already analyzed data, which hopefully will save a lot of time down the road. There's a number of ways that this needs to be expanded. I don't have polarized beam implemented yet. You should be able to use some sort of derived parameters for your marginalization, so some combination of the parameters in the model. There's some stress testing that needs to be done. There's some open questions. How wrong can your model be before things start to fail? What if you don't have a model? I think this is actually a completely different question, and we're starting to think about that now. Can you actually come up with a way of doing this that, even if you don't have a model, still gives you an improvement in your data collection rate? This is on GitHub right now. It'll probably move to the official NIST one at some point. But right now it's on my personal GitHub. You can go take a look at it. Just to wrap up then, in summary, you can calculate a real-time figure of merit from the Markov chain Monte Carlo analysis. You get at least a factor of 2 speed up over current best practices, can be much higher than that. I think there's a lot of space here to work on this. And then 2 pleasant surprises. Some regions of Q space are much more efficient than others at constraining the parameters of interest. This turns out to be true, which is really nice. And the other pleasant surprise that I think was not obvious going into this is that it also works for polychromatic reflectometry. So I would imagine for time of flight instruments and certainly on candor. So that's all I have. Thank you to all of you for coming and for your attention, and happy to field any questions.